Alrighty, good evening, everybody. I'm sorry that I'm not here today. Sorry, I guess it's good morning or good afternoon. Frankie's really sick, so I had to stay home with her today. That being said, we are going to continue moving forward. A couple of things that I want to mention before we get into today's stuff. One is that the lab that you're turning in on Friday, the lab that was due, that we did yesterday, data is really important on this one, okay? So if your data is not proving your conclusion, if you cannot concretely determine which unknown is which substance, you're gonna need to clarify that, okay? You should get 3 distinct melting points. You should be able to determine which ionic substance is which based on that information. You're going to have a melting point that occurs really, really fast, that maybe doesn't occur at all, and then one that's in the middle. If you got 2 that did not occur, and one that occurred really, really fast, you may need to redo this, okay? Because your data needs to accurately and correctly portray the fact that what you're going to try and say and claim using your evidence, that evidence is actually there, okay? So we need evidence to back up our reasoning, and if you don't have that evidence, you can redo the lab. We'll have some time on Friday when we're studying for the test that's on Monday, where you could do it in class. If you do that, you just need to talk to me so that I can make a note on your lab that the lab wouldn't be due until Monday then, to give you a little bit of time to analyze the data. But that will be something that you could do. So it's really important that you have good data. There is a way to get good data. You just have to be really careful. So if you need to redo the data, come in and talk to me, and we'll figure that out probably on Friday. Okay. So today we're going to do a little activity. It's a polarity tug of war activity. We're going to be talking about electronegativity, bond polarity, and molecular polarity, and therefore determining if a bond is going to be ionic, polar covalent, or non-polar covalent based on those electronegativity differences. Now, in an ideal situation, we would actually do this. We would do a real tug of war. Unfortunately, we just don't have that that ideal situation right now for a variety of reasons. And so we're just going to kind of talk our way through this. So in the first tug of war, we're going to have a team A and a team B, okay? Team A is going to be over here on this side, and I'm going to draw 4 team members. And team B is going to be over here on the right side, also with 4 team members. So again, this is team A, and this is team B. And you can imagine that these guys are holding a rope, and that there's kind of the center point. If I've got 4 people on both teams and they are pulling evenly, that should make sense, right? You've got the same number of people on both sides, so they should be pulling relatively evenly, okay? We have the same number of people, okay? A is going to be equal or even with B. Now, in reality, if you had these 2 teams, maybe one team is going to be slightly stronger than the other, but they should be, for the most part, even. If I took 2 of the teammates from Team B and gave them to Team A, so now Team A has 6 members, and Team B only has 2 members. we're going to go ahead and rename these teams because they've changed so much. This is going to be Team C and Team D. In this situation, you might observe or predict that in a tug of war between Team C and Team D, hope is definitely going to go towards Team C, right? It's going to be an uneven pull because we have an uneven number of people, right? C is going to be greater than D. If in my third attempt at this, Team C won, and so as a reward, I took the strongest team member here and let him pull all by his lonesome against everybody else. So you've got 1 player over here and 7 players over here. In this situation, we're going to go ahead and rename our team again because they are different. This is going to be Team E, and this is going to be Team F. You might imagine that they're going to pull him all the way over, right? It's a very uneven matchup because we have a very uneven number of people. Team E is way, way less than Team F. Okay? Imagining these teams as they are, let's rank them in order from, on a scale of 0 to 4, super wimps to macho hulks, and explain why. So if we want to talk about Team A and Team B, I would argue that on a scale of 0 to 4, they weren't super wimps. Like, right? Nobody didn't do anything. They tried. They were maybe kind of in the middle, right? So somewhere around 2.5. And if we're saying that those were pretty even, they were about equal strength. So they're kind of right in the middle. I would argue that the strongest team is going to be Team F. So they're going to get that 4.0. And one of the scenarios that we didn't show here, that I didn't talk about, but that is a perfectly valid scenario, is what if I came up as team member G and said, all right, I want to go against all of you. And then as soon as I started pulling, or as soon as we said go, I just dropped the rope and gave up. That's Team G, me, as a super duper wimp, just giving up. So Team G, who you didn't actually get to see, is 0 because I didn't even want to play. So then between C, D, and E, we would say E's probably weaker than, or the weakest besides G, who didn't even play. So let's give him a 1.0. F was definitely our strongest. That's why they got the 4.0. And then I would say D is probably our second weakest, so maybe 2.0. And C is maybe 3.5 because they were our second strongest. Okay? Thinking about all of this idea of a tug of war that we're looking at here, we're trying to kind of give you an analogy of two atoms bonding, right? Where the center line you are tugging against is the electrons that are being shared in a covalent bond, or in a bond, if you want to say. And so in our tug of war, the two teams are fighting over a rope like two atoms fight over electrons in a bond. So we are two teams fighting over a rope like two atoms fight over electrons in a bond. In this case, the two teams represent the two atoms, and the flag or the center of that rope represents the electrons. Thinking about these traits and these rankings, when we've talked about different trends or, different trends on the periodic table, what trait does the ranking represent? If you want to think about periodic table trends, periodic table trend that represented atoms fighting over electrons in a bond is electronegativity. Because electronegativity is the ability to attract electrons within a bond. And so that's kind of what we are fighting over. Okay? All right. So what I would like for you guys to do now is show you. If you turn over the page, you've got a table of electronegativity values, okay? You can see that it increases as you go up and to the right. I want to have you find what elements on the periodic table best represent teams A through G on the front. So A we said and B we said were 2.5, G was 0.0, F was 4.0. So find values over here that represent those teams, and write down the element name and about how they're going to pull on those electrons in a shared bond. Okay? I'm going to have the sub pause here for a second for you guys to work. I'm going to give 2 minutes to do this, or they're going to give you 2 minutes to do this, and then we're going to come back and share some examples, okay, or some possible answers. There's not necessarily one right answer. So if the sub could pause this video for 2 minutes, please. Okay, so hopefully you and your table group found some examples. We could go through, and these are some possible options. So we said team A was 2.5. Looking here on our table of electronegativities, sulfur is 2.5. And then, let's see, iodine is also 2.5. So team B could have been iodine, because they were about the same strength. We said team C was like 3.5, which could be oxygen. It had a strong pull, team C did. Team D did not pull very strong at all. We gave that I think it was like a 2. A 2. And so an example of that, something like boron, because they had a weak pull. Team E, which was the weakest pull, we said that was something like a 1. That could be something like lithium. And then team F is something, we said it had a pull of 4. That would be something like fluorine. It had the strongest pull. And then something for team G, that would be like helium, neon, or argon, which didn't even interact. They don't even have electronegativity values listed, okay? So what I would like you to do now is to go through and read this section about electronegativity differences in the tug of war for electrons. Calculating that electronegativity difference is what determines if a substance is non-polar covalent, polar covalent, or ionic. So if an electronegativity difference is less than 0.4, these are non-polar covalent. The electrons are shared equally. If the electronegativity difference is between 0.4 and 2.0, it is unequally shared. The electrons tend to count on one side more than the other. And if it is greater than 2, then the electrons are transferred. They're stolen or lost. And so that's more of an ionic bond, okay? Less than 0.4, 0.4 to 2, and then greater than 2.0. So go ahead and read this, and would like you to answer the question on number 16, where you are going to be determining the types of bonds between different atoms. Before we do that, we're going to just really quickly go through some notes that I'd like to do with you. And then I'll give you time to work on that, and then we'll do some intermolecular forces notes. So polarity, all this that we've been talking about right now, polarity is when elements with different electronegativities, so elements with different electronegativities squeezed that in there, or En for the future, share electrons unequally. There should be 2 L's there. Unequally. So in a covalent bond, we get what we call a polar bond when elements with different electronegativities share electrons unequally in a covalent bond. Remembering that electronegativities is an atom's, hopefully you can see that, an atom's ability to attract electrons within a bond. When this happens, when we have this unequal share of electrons, this creates what we like to refer to as a dipole, where we get a slight positive and slight negative ends within a bond or even within a molecule. So for example, if I have HCl, right? HCl is a hydrogen with 1 electron and a chlorine with 7 electrons, okay? When those bond together, we can see what type of bond it is. If I look at the electronegativity of hydrogen, which I can find on that last page, right? The electronegativity of hydrogen is 2.1. The electronegativity of chlorine is 3.0. So with that in mind, I'm so sorry, you guys. It's really late. With that in mind, Hydrogen is less electronegative than chlorine. Chlorine is more electronegative. Because chlorine is more electronegative, in that pull, in that tug of war, the electrons are being pulled closer to the chlorine. And so because of that, the chlorine gets a slight negative charge, okay? Whereas hydrogen, because it's weaker, the electrons aren't hanging out around it as much in the bond, they're hanging out more with the chlorine. It's missing out on that negativity, so it develops a slight positive charge because it has less electronegativity. All right? That is because the more electronegative is, of course, chlorine, because it is better at attracting the electrons, and since electrons are negative, it gets, oops, there should be an S in there. Sometimes I start my other word first. It gets a slight positive or slight negative dipole because it attracts the electrons more and the electrons are negative. Okay, so you'll notice a couple of symbols here. We've got this slight. That's a lowercase delta. It means slight or partial. I'm sorry, you guys. Like I said, it's real late. It may not be late for you guys, but it's late for me. A slight or partial charge, it is not a full charge, right? We are not creating an ion, we are creating a dipole, a slightly negative or slightly positive charge. And then oftentimes what we'll do with this is when you have this bond, you'll want to show the what we refer to as a dipole arrow, like which way is the dipole pulling. And for that, we do a special arrow that has like a start symbol, a plus pointing towards it. It's called a dipole arrow, and it starts at the positive. So you start at the slight positive because there's a positive, and you end at the negative. Okay? Again, when we're going through this, if we're talking about electronegativity, if the change in electronegativity difference, or the difference in electronegativity is less than 0.4, that is a nonpolar covalent bond. If it's between 0.4 and 2, it is polar covalent. And if it is 2 or greater, it is ionic. Okay? I'm going to have you guys take kind of a 10-minute break from taking notes, or 5 to 10 minutes. I'll let the sub kind of judge on this and work on question number 16. I'm going to have these notes scanned in online, so if you need to reference them, you can take out your laptops and do that, if like you missed anything. But I'm going to give you like 5 to 10 minutes to work on question number 6, and then we're going to get into our next topic. So if the sub can please pause this video for about 5 to 10 minutes, it's your call. Okay, everybody, we're moving right along. So the last kind of bit of information that we're going to learn in this unit is something that we refer to as intermolecular forces, or IMFs. Sorry. Woo-hoo. I stopped moving. We've been talking a lot this unit about different types of bonds, ionic bonds, covalent bonds, all of that. And we just talked about polarity and electronegativity differences and how that determines whether a bond is ionic or covalent, or more specifically, ionic, polar covalent, or non-polar covalent. And now we're going to look at another type of attractive force, then not a bond. And that's really important to recognize. We've been talking a lot about bonds. This last thing that we're talking about is not a bond within a molecule. We are talking about, if I have these molecules, how is it that the water molecules stay together in a glass of water, right? How that they're not just like floating around away from each other. And so that is about a force between molecules, not within molecules, okay? And so that's what we refer to as intermolecular forces. So intermolecular forces. Or, as they are often referred to as, IMFs. These are the forces, not bonds. I'm going to go ahead and give that a nice big circle to remind you guys. These are forces, not bonds, between molecules that hold molecules together. There are three types. We're going to refer to those three types over here on the right. Okay? Intermolecular forces are responsible for the phase of a substance. They determine whether something is going to be a solid, a liquid, or a gas. Okay? So if you think about intermolecular forces as forces of attraction between molecules, if I have molecules that are very close together, if those molecules are very close together, that's because they have really strong intermolecular forces, or high intermolecular forces. That's keeping them together. That attractive force between the molecules is strong. It's holding them all together. If I have a liquid where the molecules can kind of flow a little more around each other, they're still close, but they're getting further apart. That's a liquid. It's got weaker IMFs. And in a gas, where those molecules are just pinging all over the place, they're very far apart. The molecules are very far apart with basically nothing, in air quotes, holding them together. We have basically no intermolecular forces. I have to say basically or approximately, because there you have to have some sort of intermolecular force. It's so incredibly weak. When we are changing the phase, water, for example, H2O, can be solid, liquid, or gas. When we are going from a solid ice to liquid water, when we're melting, that means we are weakening our IMFs. When we go from liquid water to steam, gaseous steam, or boiling, we are breaking those IMFs. Okay? So that's what intermolecular forces are, kind of the general bit about them. The next thing we need to figure out is what are the different types, okay? So you'll notice here in the center, we've got kind of an arrow pointing down. There are 3 different types of intermolecular forces, 1, 2, and 3. The one up here at the top is our weakest. The one at the bottom is our strongest. Okay? We're going to talk about them individually. I'm going to zoom back in. The first one, our weakest intermolecular force, we refer to as London dispersion forces. Or LDFs. If you're looking at other videos or other online resources, you might see these referred to as van der Waals or van der Waals forces. Anything, just name. London dispersion forces are the weakest, but they are also the most predominant. They occur between all molecules and atoms. Okay? Everything experiences London dispersion forces. So they occur between all molecules or atoms. And at this point, it would probably be a good idea to mention the fact that different substances or different molecules can actually have more than one intermolecular force of attraction existing, because they all have London dispersion forces. But along with those London dispersion forces, they can also have the second type, or they can also have the second and third type, okay? Everything has London dispersion forces, but they can also have the others as well. London dispersion forces are created when instantaneous or temporary dipole occurs. So it creates an instantaneous or temporary dipole. So in those tug-of-war notes, when we talked about polarity, we said that dipole is a slight positive or a slight negative. That is a permanent dipole, because in that bond, that is always that way. The chlorine is always pulling harder than the hydrogen. London dispersion forces happen when molecules move close to each other and cause a temporary or instantaneous repulsion of the electrons, kind of moving them to one side of the atom or the molecule more than the other. So it happens when electrons move closer to one side of a molecule or atom for a moment. So for a moment, our atom, instead of being a sphere, becomes more of an oval, and I've got my protons or my positive charges on the left and my negative charges on the right. This creates a temporary dipole, which when next to another molecule experiencing this same kind of phenomenon, there's going to be an attraction between the slight negative end of one molecule and the slight positive end of another molecule. And so they kind of realign themselves so that their slight negative and slight positive ends are attracted to each other. So this attraction between these molecules, between the slight negative, slight positive ends of different molecules, that is your London dispersion force. This is going to occur in molecules that are symmetric, meaning they look the same in three-dimensional space, okay? If a molecule looks the same in three-dimensional space, it is considered to be symmetric, and it's going to have London dispersion forces. Frequently, we are asked to rank substances in order of their intermolecular force strength, and sometimes you have to compare substances that have the same intermolecular force. So if we're trying to look at comparing London dispersion forces to each other, if you increase the number of electrons, meaning you increase the size of the molecule, you increase the strength of the London dispersion forces. So that's our first intermolecular force, London dispersion forces. The second one is called dipole-dipole, or DD. Dipole-dipole is the middle child here, right? It's stronger than London dispersion forces, but weaker than the third one. Dipole-dipole, as you can imagine, hence the name, it's got a dipole. It occurs between polar molecules. This is why we had to have that discussion about polarity before we could discuss intermolecular forces, is we have to think about what makes a polar molecule, right? That hydrogen and chlorine that we did the example with, that was a polar molecule where the hydrogen is slightly positive and the chlorine is, the chlorine is slightly negative. But this is, unlike London dispersions, this is a permanent dipole, not a temporary dipole. This is a polar molecule. This has a permanent pole or dipole. And therefore, between molecules of HCl, you'll have an attraction from the slight negative chlorine on one molecule to the slight positive hydrogen on the other molecule. And you'll see that play out as these dipole-dipole forces of attraction. Dipole-dipole interactions, or dipole-dipole IMFs, occur in asymmetric molecules. Molecules that do not look the same in three-dimensional space, right? In the HCl, we have a hydrogen on one side and a chlorine on another. That is not symmetrical, okay? Or symmetric. Same way that we tried to explain how London dispersion forces can be stronger or can compare to other London dispersion forces. In dipole-dipole molecules, the bigger the difference in electronegativity, like the more polar the molecule is, the stronger the dipole-dipole force. So if you increase the difference in electronegativity, you increase the strength of your dipole-dipole, IMFs. All right, so that was our middle child. Now let's talk about big brother. This last one, the strongest of the intermolecular forces, has the most annoying name, because one of the things that I said at the very beginning is that these are intermolecular forces of attraction. They are not bonds. And yet this last one is called hydrogen bonding. Or H bonds. Okay? This is still not a bond. Okay? It's still not a bond. We call it hydrogen bonding because it occurs in molecules that contain a certain type of atom bonded to a hydrogen. That's why it's called hydrogen bonding, is because this bond between hydrogen and a different type of atom has to exist within the molecule in order for hydrogen bonding to occur. So it occurs between polar molecules. So same as dipole-dipole, but specifically polar molecules which contain a nitrogen, hydrogen, oxygen, hydrogen, or fluorine hydrogen bond within the molecule. Okay? You guys know I love my dumb phrases to help you guys remember stuff, to help you remember which other atoms or which other elements have to be bonded to hydrogen for hydrogen bonding to be considered true. I have two phrases for you. One, if you're enjoying this, if you're like, man, this is kind of cool, this information is fun, you can say, hydrogen bonding is fun. F-O-N. It's fun. Fluorine, oxygen, nitrogen. Or, if you've had just about all you can stand of my puns and dumb jokes, you can say, I've had enough hydrogen bonding. Enough. N-O-F. Okay? You're welcome. It's dumb. That's why you'll remember it. Okay, so these are polar molecules, just as we talked about with dipole-dipole. If we want to take a look at it, the example that I give is water molecule, which has a hydrogen or two hydrogens and an oxygen. The hydrogen electronegativity is 2.1. The oxygen is 3.5. So oxygen is more electronegative, which means it's going to have the slight negative dipole, and the hydrogens are going to be slightly positive. So my hydrogens are slightly positive. My oxygen is slightly negative. And then just as with dipole-dipole, and also just as with London dispersion forces, there is an attraction between the slight negative of one molecule with the slight positive end of another. It's just that these hydrogen bonding has to occur when the hydrogen and oxygen, or hydrogen and nitrogen, or hydrogen and fluorine are bonded together. And then kind of similarly to London dispersion forces, where the bigger the molecule, the stronger the intermolecular forces, the stronger the LDFs. The more hydrogen bonds there are within a molecule, the stronger the intermolecular force, the stronger the hydrogen bonding, okay? So the higher the number of H bonds in the molecule, you have the higher the strength of the H bonds. Okay? All right. I'm going to be done talking to you guys. You're going to have the rest of class to work on the homework for this. I have some intermolecular forces homework. I'd also like you guys to take a quiz. Actually, I'm going to save the quiz for Thursday. So I'm just going to have you work on the homework. You can work on, again, question number 14 from the dipole, the polarity tug-of-war. I'm going to check that off on Thursday. And then you can also work on the homework, which I'll have the sub handout, which is Intermolecular Forces of Attraction. This last little bit over here, we're actually going to talk about after we do the pivot lab that we're going to be doing on Thursday. So please remember, on Thursday we're doing a pivot lab, that thing that I made you sign up for before Thanksgiving break, like way before Thanksgiving break. It's this online lab where we watch people do a lab and we like collect data with them and answer questions. The lab itself is using chemicals that are too dangerous for us to use. And so, but we still want to gather the data and look at kind of analyzing it. So it's looking at the intermolecular forces of attraction, the IMFs, and comparing how that affects the boiling point of different substances. So we'll finish those up after you guys have actually worked on that pivot lab. Okay? So that's what we're doing on Thursday in class. We'll do the pivot lab, we'll take the quiz, and then Friday is going to be a review and another quiz, because you haven't been quizzed enough. And having that like extra week off of school kind of jam everything up together. So if you've got questions, ask them. There should be some scanned in notes from what we just did here on Canvas. So take a look at Canvas if you need to. Fingers crossed, I'll be back at school on Wednesday. If you have questions that you can't wait until Thursday, my husband said he could take off Wednesday if Frankie's still sick. So I should be back on Wednesday. Thursday at the latest. Thank you guys for your patience. Get to work. Be good.